Hello, welcome. By the end of this video, you should be able to, firstly, define the term relative atomic mass, very simple. Secondly, calculate the relative atomic mass of an element when given the abundance of its isotopes. Hopefully by now you know what isotopes are. So let's get started. The first thing is to understand what it means to calculate a relative atomic mass. So let's look at these two isotopes. We're going to annotate the atomic numbers, the mass numbers, and the overall nuclear notation for these two atoms that we see here. Let's begin with the atomic number. You remember the atomic number is the number of protons in an atom. Here we have the protons are the purple guys. We have 1, 2, 3, 4, 5 protons here. And if you pause and count there as well, you see we also have 5 protons, which means these are fundamentally the same element. But let's look at the mass number. The mass number is the number of protons plus neutrons, or the number of nucleons. Here we have 1, 2, 3, 4, 5 protons, and then also 5 neutrons. So we have then 10 nucleons, a mass number of 10. Here on the other hand, we have 5 plus 1, 2, 3, 4, 5, 6. So we have 6, sorry, not 6. We have a mass number of 11, okay? That's the 6 plus the 5 gives you a mass number of 11. Therefore, now we can put the nuclear notation. If it has 5 protons, if you look at your periodic table, which you should have memorized maybe by now, at least the first 20 elements, you should know that an atom with 5 protons is indeed boron. And this is boron 10, and that one is boron 11. Okay, so these are two isotopes, and if you want, we could put also the number of protons under there, although that is somewhat redundant. Here is that in a neater form if you want to copy it down. Now the thing is, these are two different isotopes of boron, and it turns out that both of these isotopes occur in nature. So when boron was formed a few billion years ago in some exploding star, both these isotopes were stable enough to be formed. So we have both of these in naturally occurring samples of boron. This creates a bit of a problem for us. Here is the problem. If I give you now a mole of boron and I ask you how much does it weigh, you're going to have a hard time giving me the answer. How so? Well, if we knew that this mole of boron was just boron 10, that is all the atoms in that mole of boron were this, then its mass number, its weight would be 10 grams. So that's how a mole works. A mole is the number of particles that's needed to take the mass number, which is the number of massive things, and convert it to a value in grams. It's just an arbitrary number that humans picked. Okay, so if we knew that was boron 10, then it would weigh 10 grams. If we knew that was all boron 11, it would weigh 11 grams. But it's both. So what does it weigh? Does it weigh 10.5 grams? Maybe 11 plus 10 divided by 2? No, because that would be what? That would be a simple average. What we need is a weighted average to take into account the relative abundances of each of these isotopes. Where do we get those relative abundances from? Well, we get them from something called a mass spectrometer, but I'll talk about that in a second. Let's look first at an analogy to how we do weighted averages. So here we have now a set of basketball players. We have 9 of them, and they're all 2 meters tall. And we have that short guy there who's 1 meter tall. He looks like an alien. Now the question is, what's the average height of this basketball team of 10 players? Is it 1.5 meters? No. That will be the average height of just these two folks. So what we need is a weighted average. How do we do this? We're going to multiply the abundances or the proportions of each type of player by the heights and add them up. So we have 9 out of 10 of them are the tall guys. So we have 9 over 10. Which is the same as 0.9. You just move the decimal place 1 place back to get rid of this 10 under. So we have 0.9 times the height of 2 plus 0.1 times the height of 1. Okay? We multiply that out, do the math, and we get a value of 1.9, which seems like a more reasonable value. This is the weighted average of this group of basketball players. So it'll be somewhere about here. All right, so it reflects the fact that most of them are tall. Let's get back now to our example here with boron. So what we need is we need to know what's the relative abundance of these two types of isotopes in that sample in order to figure out its weight. or its relative atomic mass. To do this, we use something called a mass spectrometer. You don't need to know how it works at the moment. All you need to know is how to read the graph. And the graph is basically just a bar chart. So you look here on the m/z axis here, and you can read out the mass number. So we see that the thing with a mass number of 10 has an area under the peak, or basically the height of this of that line, of 19.8%, and the other one of 80.2%. So now we know the relative abundances of these guys, and just like with the basketball players now, we can calculate the actual weighted average of these masses. So how do we do it? Just like before, we're going to multiply the abundances by the masses and add them together. So here it is. We take 19.8% and convert it to a decimal. So 19.8% is the same as 19.8 per cent, per hundred, per cent or hundred. Cent is 100 in French and in Latin, I guess. Okay, so we remove those two zeros, and that would go 2 places back. So we end up with 0.198. 0.198 times the mass number of 10 plus 0.802, which is 80.2% as a decimal, times the mass number of 11, and we do the math, and we get out 10.802, and that's our relative atomic mass. So if we have that mole of boron then, and we ask how much does it weigh, well, it weighs 10.802 grams, because that is the weighted average of these two mass numbers. So 6 hexillion, you know a mole is 6 times 10 to the 23, which is 6 hexillion. Why is my pen not working? What's going on? Oh, I turned it off. Oh, jeez. Let's see what's going on. All right, 6 times 10 to the 23. That's 6 hexillion atoms. So if you have 6 hexillion atoms of boron, on average, it would weigh 10.802 grams. And here is the value you see in your periodic table. It differs slightly from what we've just calculated. There's some reasons for that. We won't go into it. What we will do now is define then the relative atomic mass. So you might be asked for this definition. You might be held responsible for it. The relative atomic mass we define as the weighted average. That term you already understand, a weighted average versus a simple average, okay? Of the masses of the isotopes, you know what isotopes are, of a naturally or in a naturally occurring sample of the element. It needs to be naturally occurring because in theory, you could get some boron that was pure boron 11. You could isolate out all the boron 11 atoms. There are a number of mechanisms to do that, and you wouldn't have a relative atomic mass of 10.801. You'd have a relative atomic mass of just 11. And we wouldn't call it a relative atomic mass. So you need the naturally occurring sample of the element. And we standardize that relative to 1/12 the mass of an atom of carbon-12. It's a bit dicey to explain why we use 1/12 an atom of carbon-12 as the standard, but just think of it as 1/12 of the mass of carbon-12 is just 1/12 times 12, which is just a fancy way of saying 1. You can think of it that way for now. You might see some synonyms of relative atomic mass. Atomic mass is one synonym. Atomic weight, relative atomic weight, they all mean the same thing. Okay, so now I think we know how to calculate this relative atomic mass. Let's have you try this one. Pause the video and give it a go. And in 3 seconds, I'll read through it and then try to answer it. 1, 2, 3. Hope you pause it. So it says a sample of the element magnesium contains 78.70% magnesium 24, 10.13% magnesium 25, and 11.17% magnesium 26. Find the average mass of magnesium atom to 4 sig figs. How do we do this? Well, we multiply the abundances by the mass numbers, and we just do the math. So here we have now 0.7870 is that thing as a decimal. We just move the decimal place 2 places back. This one is that as a decimal, move the decimal point 2 places back, and that one as well. And we multiply each by its respective mass number, 24, 25, and 26. We plug this into our calculator, and we get these values and a final answer of 24.32. That is our relative atomic mass then, or that's the average mass of a magnesium atom to 4 sig figs. Nice. Let's try another one. It says, a sample of an element is analyzed on a mass spec. The readout is shown here. Calculate the relative atomic mass of the elements and determine which element was analyzed. So pause the video and try this one. In 3 seconds, I will go through it. Hopefully you've paused. 1, 2, 3. So here we have 3 different isotopes. 28, something 28, we don't know the atom, 29, and 30, and we have the percentage abundances. So what do? We take each of these percentage abundances, multiply them by their respective mass numbers, right? So here we have 92.23% as a decimal times 28, and then that one as a decimal times 29, the next one as a decimal times 30. And we just do the math and we get a final answer 28.1. Now, how do we determine which element was analyzed? Well, you just need to go to your periodic table and look for something that looks like it has a relative atomic mass of 28.1. And the closest you will see to that will be silicon. And that would be your answer. So hopefully now you get the general idea for doing these. It's really quite simple, so we won't spend too much time on it. All you do is you take the percentage abundance, you multiply it by the mass number of each isotope, and you add them together and you get a final answer. So I'd say now that we've covered both of these objectives, I can define the relative atomic mass, hopefully you remember that definition, and I can calculate the relative atomic mass of an element when given the abundance of its isotopes. You might need some more practice on this. There will be practice questions on the website, but until then, or until the next video, I will bid you farewell. Bye-bye.